welcome to the last half day of the workshops. Tomorrow is a holiday. Cesar Chavez Day. That's what officially is. We have a good lineup of 3 speakers in this immediate session. Leading it off is Devavrat Shah, time series analysis of matrix estimation.
Thanks, Balaji, and thanks organizers for putting the meeting together. I'm going to talk about a class of questions which I would call time series analysis, classical questions, and I would like to use a method of matrix estimation to solve these questions. As the talk will progress, I'll make it clear what questions I'm talking about in the context of time series analysis, and in case you have not looked at the matrix estimation method, I am currently a big fan of that. It's a fantastic method that's out there that's been utilized, developed collectively in over the last decade or so. And I will describe that in briefly, and then we'll put these 2 things together as a part of the talk. This is based on joint work with 3 of the students at MIT, and those are the papers associated with the talk. Okay, so let's start with just a sample questions to explain what these time series analysis questions are. So I'm going to talk about questions from retail because I've been close to retail over the past couple of years, and I think retail is fascinating, at least right now. So here's one question. So let's think of a Target store in Sunnyvale. Initially, I was going to think of Target store in Palo Alto, and then I realized that sounds like a wrong thing. So let's say Target store in the Sunnyvale, and there is one in Sunnyvale, by the way. And it's nice weather like here, and you're selling umbrellas in that store. Most likely, those umbrellas are hardly selling, first of all. And maybe when it was rain like last week, maybe there was a surge in umbrella sale. And then maybe there were 4 umbrellas on shelf, and because there was too much rain, all of them got sold out. And then there are a few days where you don't have any demand recorded because there are no umbrellas available on shelf. So effectively, what's happening is that you got a few, let's say every week, you're observing some number of transactions of umbrella sale. And these are integer numbers. They're censored. Hence, you might have lots of missing values. And what makes sense as an underlying model is there's a latent demand or latent rate that's changing over time. Okay, and what you want to do is that you want to estimate a rate like that. There's an underlying hidden structure from these kind of extremely noisy data. Another question, well, now that you sort of estimated what happened in past, maybe you want to predict what's going to happen in future. Maybe there is a trend, maybe there is a seasonality, maybe there is some kind of a stationarity, or combination of all of that. And then finally, if you are somebody who is providing solutions to these retailers and you say, hey, you guys should use my policy, whether that policy for mobile checkouts, if you call it, or if it's a policy saying that this is how you should stock your inventory or whatnot, at the end of the day, I would say, well, I'm going to give you these amazing decision rules because of which your revenues are going to go up. And then your customer, in this case Target, will say, well, I'm not sure actually your policy is going to make any difference to me. Actually, it might ruin my thing. And then now it's onus is on you to prove to them that, no, actually it's going to work well. They say, OK, that sounds fine. What I'll do is I'll create 2 copies of Sunnyvale Target store. In one, I will run the policy, and another, I will not run the policy. And as you're listening to this, they say, well, that doesn't make sense because there's only one Target store in Sunnyvale. So then the question is that how do you deal with this kind of question? It's like saying the question is whether a given policy like gun control is going to reduce the crime rate or not in California. Well, there are no 2 Californias. It's not like classical randomized control. So you need to somehow create a control out of a thin air. And as economists, this is a beautiful topic, especially in econometrics, has been studied more so in the last decade or so under the umbrella term called synthetic control. And their basic idea is that, well, yes, Sunnyvale is only one store, but maybe there is another store in Mountain View, which there is, which is almost like Sunnyvale. So maybe let's implement a policy in Sunnyvale and not implement policy in Mountain View, and then see what the differences are, or a combination of that. And the question is, how do you do that in a data-driven manner is what's a really interesting set of questions. So anyways, these are the 3 questions that I want to consider in this talk. And just to summarize, right, really, on one hand, I'm trying to understand that there is some notion of state that is hidden or latent that's evolving over time. And I want to estimate that when observations are extremely noisy, like I've got a noisy Poisson noise, for example, or n/or missing values, and question how do I recover that? In addition to just recovering the unknown state, can I predict what's going to happen? That's a forecasting. And then finally, the third thing is how do you think about synthetic control? Okay, so those are the three questions. Any questions about the questions? Okay, all right. So those are the three questions. That's a time series analysis part of the title. And now I'm going to talk about matrix estimation. And this is something most of us have seen. I'm just going to quickly do level set. I'm going to walk through that. One way to think about classical matrix completion or Netflix recommendation question is that you've got users, you've got movies, you've got a bunch of ratings between users and movies that are observed, and lots of them are not observed. And what you want to do is that you want to estimate the missing values n/or you want to actually denoise the observed values. Okay. And that's basically a matrix estimation problem. Putting it other way, there is some ground truth underlying matrix A that you want to estimate so that your error is small. And to estimate this, the observations you have is effectively, let's call it a matrix Y, where the entries Yij has something to do with Aij, and not all of them might be observed. Okay, so in a sense, you've got noisy version, noisy plus missing value of matrix, and from that you want to recover the original matrix. Okay, so that's basic matrix estimation problem. Here is a generic model that's useful to encompass a large class of things that are done in this literature. On one hand, the classical matrix completion question in the context of recommendation system, or stochastic block model for community detection, or graphones more generally, or effector models that economists think about for things like synthetic control, and the list goes on. Okay, so all of those things effectively boil down to this kind of a nice, clean, simple model, where the model says that every row and every column of your matrix has some hidden features. Let's call it x1i and x2j. The ground truth that you want to estimate is, again, some latent function applied to these latent features. That's aij. So the function is consistent across all entries. And in a sense, matrix is now parameterized by these row column features. And observations that you have, which is Yij, is such that you don't know the distribution, but you know that in expectation, it is Aij. Okay. And usually, in this literature, one would assume that Yijs across Ijs are independent. If it's, again, classical matrix completion literature, one would say that Yij is Aij plus additive symmetric noise with zero mean. Or if it's a graphon setting, then you would say, well, Yij is 0 or 1 with probability Aij, et cetera, et cetera. Okay? And there's great sets of reasons why this is a very good model. Again, and given this setting, what you want to do is that you want to understand under what structure on the function feature space and the amount of data you observe, you can actually produce a consistent estimator. Okay. Any questions about the matrix estimation as a question? All right. And there are roughly two types of things. Again, this is a little more detailed than what I want to talk about, at least for the purpose of this talk. But highest level, either it's additive or this is generic noise. And the purpose of this table is to say that there is lots of nice work that's done over past a decade. And there's a extremely large literature. It's like I could sort of just keep talking for the rest of the session. But I'm just putting out for each pair of noise model and function class, what are the best sample complexity results known. For example, this is by Keshavan, Montanari, and O. That's by Chatterjee. Those two are by some of me and my collaborators. Okay, but the point that I want you to take away from this is matrix estimation is at a reasonable place where there are good algorithms that are out there, and we do understand the thresholds and sample complexity reasonably well. Okay, and the main point of the talk is that, well, all the three questions that I spoke about in the beginning is the time series analysis question, that is estimating latent state, forecasting the state, and producing a good synthetic control. All of them can be solved by matrix estimation. Okay. So for the purpose of talk, I'm going to assume that there is a nice black box method, which is good matrix estimation method. And what I want to do is really, I want to show you how each of these problems can be viewed as a matrix estimation problem. Okay. Right. So with that, let me just get onto the details of it. Okay, so first is what I would call time series imputation. And again, it's an imputation because there's a latent structure that I'm not observing because of noise or because of missing value or both. And hence, I'm trying to impute it or interpolate it, putting it other way. And here's, depending on how you look at it, at least this one way to do time series analysis in econometrics literature, which is where this is, at least right now, at least for me, among my colleagues, that's where the home is for this. The standard practice would be, well, you look at your time series data, and you say, well, let me see if it's stationary or not. If it's not stationary, let me find out non-stationary component. One way to find that out or remove that is to fit some kind of a sparse polynomial basis to that and get rid of it. Okay. Once I'm done with that, so now I'm in the world of stationarity, but then I'm involved in stationarity and periodicity. So let me get rid of periodicity. And then finally, I'm done with that. Let me go to some form of stationarity. Okay. And then sort of layer by layer, I'm going to take my data, peel them off. There are all good tests around it to sort of determine how to stop and so on. But there's some human intervention. But at the end of it, you come up with a nice model. And that's effectively what a good R library package for time series analysis would do. And for the purpose of all the results I'm going to state, I'm going to assume that underlying function f that's of interest, indexed by t, is one of these models or combination of that. Yes? Any questions? Okay, so f of t is my interest. I'm going to recover it. And my observations are these random observations x of t. Okay, and the way these random observations are is that in expectation, it's f of t. So for example, again, x of t could be f of t plus additive noise with 0 mean, or x of t could be just a Poisson random variable with parameter f of t, or any such thing. Okay.
So just the umbrella example, where you ran out of umbrellas.
Yes.
X of t is what? Not the number of umbrella orders, because the number of you only have sales receipts.
Perfect. So, okay. So, for example, let's go back to that umbrella example. One model, not necessarily the model, but one model could be that, well, there is some notion of, let's say this is, let's think of t as indexed by week. Let's forget sort of it's an integer time step. And f of t is the rate at which umbrellas are supposed to be sold, or the true demand for umbrellas at time t. And the way it's going to be realized is that every time, the number of people who want to come and buy umbrella is some Poisson random variable with that parameter. Okay? And you're going to observe x of t. Now it's possible that, and that's simply based on transactions.
Right, but that's who comes to buy. But then the unmet demand is not.
So for example, if, okay, we didn't have conversation before, but thank you. For example, if C is my shelf capacity, or the number of umbrellas on shelf, then I'm going to observe x of t, which is something like this. Perfect. And then from there, I know C. I know effectively this g of t. G of t is what I'm estimating. Maybe from g of t, I would like to go back to f of t. And of course, Poisson is a nice function, so inversion is easy. And it's and so on. But effectively, we'll estimate g of t well, and then from there, maybe we want to go to f of t. That's great. Thank you. Any other question? Okay, so this is like if you think of classical linear models which are hidden structure, then there will be again a special case of that, and so on. All right, so here's the algorithm. Again, x of t is my data. Here's what I will do. I'll explain you what the transformation is to taking this one-dimensional data into a matrix. Then we'll apply the matrix estimation method that we borrowed from literature that we all agreed for the purpose of the talk. There's a beautiful method that exists out there. And then just do undo transformation, and that's it. So really, all you're doing is matrix estimation. Okay. All right, so, and it's as dumb as it gets. So this is, let's say, my time series. Okay, and I'm assuming that this could be not observed, and it's okay. But I'm going to sort of put something. And something would be just, let's say, empty or question marks. So this is my time series. I'm going to choose some parameter L. And then I'm just simply going to divide my time series into these non-overlapping blocks. And these would form my columns. So this is first L thing are my first column, second L things are my second column, and so on. And that's it. And now this is my matrix. On this matrix, I will run my matrix estimation algorithm. Let's call it that produces some matrix M hat or M. And that's and then of course then I know that sort of this value in that matrix, this is a good estimation of f of 1, f of 2, and so on. And that's it. Any questions?
So L is picked arbitrarily?
L is picked arbitrarily right now for the purpose of the algorithm. The question is that how do you pick it? I'll tell you in a second. There is one relationship that you want to maintain. Okay, so let's do that for a second. So what you want to do is you want to make sure that the way that is the universal choice is that you want to make sure that L and T obey the relation that L square is roughly T. That is, if you have T, then you have T raised to 1/3 is L, and T raised to 2/3 is the other dimension. Great question. So yes, sir. Thank you. The question is that do I need assumption on rank of the matrix because the traditional literature in matrix estimation or matrix completion in particular assumes some kind of a low rank structure. So answer is no, and I'll explain you why. Okay, so this basic insight is that this matrix, the way it's formed, if indeed F satisfies one of those model classes or combination of there, then this matrix would turn out to satisfy that latent variable model that I explained, and latent with Lipschitz functions. And if this is function class, then it's not exactly low rank, but it's not too far. That is, for Lipschitz functions, we know how to do matrix estimation well as well. Yes?
So in the matrix model, there's the I and J. So
yes.
Supposedly the row and column determines the distribution or the mean of the entry. Is there some intuition as to why x2 should be related to xl plus 2 in this case? The second row, why are they related?
So again, remember, all of these x's are generated, at least in expectation. They're nothing but that function f. And hence, there is some relationship. But it turns out that even though they're like, sorry?
L so far is some kind of arbitrary.
Some kind of arbitrary. Yeah, and so I'll come to that in a second. So let's assume for a second that sort of I've chosen L well. Independent of whatever choice of L is, this matrix will satisfy a latent variable model.
The complexity presumably would depend on, like, you can make bad or good choices as well. But
good. Hold on to that for 2 slides or 1 slide. Okay. Yes.
Just a quick question. So are these measurements equally spaced, or there's no such assumption?
So in this case, I'm assuming that they're equally spaced because I'm sampling them at integer values. Okay. Now, of course, at some integer value, I may not observe it, and that's okay. But still, I will know that there is a notion of a time unit. Yes?
There's a latent variable model behind trivial here. It's just f of ij is f regardless of I and j.
The question is, what is xi and xj, x1i and x2j? It would be no. It'll have to depend on f, but it'll be some transform version of that. Because f is one-dimensional function, latent variable model is two-dimensional function, so you'll have to do something.
But into the earlier question about it's sort of arbitrary, the columns and rows, like why would it?
Okay, so let's let me paraphrase your question. Why would a latent variable model be satisfied here when I sort of organize this matrix this way? All right, so quick answer now, and maybe in interest of 6 minutes I have left, is, okay, let me answer that question at the end of the talk. Thank you. I should have figured out a way to answer that briefly. I'm sorry, I have not figured out that yet. Okay, so, all right, so here's the basic theorem, and again, details are missing in a sense here, but let's just sort of do one thing. Let's just go back to the classical signal processing world, right? Where I've got, let's say I've got 1 to n different periods, and in that case, really I'm solving, if it's noise-free, then I'm solving system of linear equations with 2n parameters, okay? Because sines and cosines are fixed and known. And then, of course, if I add noise, I'll need scaling, which is faster than n, okay, when I'm thinking of additive noise. Okay? What we need in this case is t should be n square, okay, not n square, so this is a quadratic loss. Is this good or bad? Again, sort of our interest getting into this was not we want to win a race, but we want to have a generic method that works across class of models. But I do believe that there is something here, maybe not n, but something more than n that is needed, because this kind of theorem works for even Poisson-like noise, while this kind of result requires you to have additive noise. So denoising, depending on noise model, can be complicated, and that might require more data. Okay, so I don't know what's the right lower bound here. I believe that right lower bound should be n to power alpha, where alpha is strictly greater than 1. Definitely it's less than 2, but I don't know why. So that, in a sense, Ramesh briefly answers, at least in the specific model. And for each class, you can figure out, and for depending on, there's a formula there. Okay, here is one quick experiment. What we did is, again, we took a nice mixture of all 3 models. It was additive noise. And what I'm plotting here is the fraction of data observed randomly. And what I'm plotting on that axis is mean squared error. And again, this is normalized. We normalize all data to lie in between interval -1 and 1. And this is the error that you get with our algorithm across P. This is the error that you get, what I would call baseline, and baseline comes from R. And this is what you would get using Amelia. So Amelia, if you have not heard of it, it's one of those things which all the empirical social scientists swear by. And it's a nice model in the sense that they assume that there's some notion, some kind of a Gaussian model, use that to interpolate through EM algorithm. Okay. So at least it's not doing terribly. Here is, at least I found this more interesting. So let's see, what did we do? The same time series, but now instead of observing an additive noise, we are generating a Poisson noise. Okay, so we made sure that sort of everything is positive first, and then generated a Poisson. And then this is shifted back, so, okay. And then what these gray things are actual observations. So as you can see, they're all over. The blue is true means or true time series, and the red is the estimation. Again, I hope you're seeing very little red. So this seemed to do really well. Okay, and that's just to say that sort of there's a, with increasing P, the R square and RMSE are going in the right direction. Okay, so that's the first question. Now I have 2 more minutes, right? Okay, thank you. So let me quickly go through this second and third part. Again, let's assume the same model as before. And now instead of just doing imputation, I want to actually forecast. That is, given data till time t, I want to predict what's going to happen at time t plus 1. Okay. And here you do one more step. And one more step is, in addition to doing transformation and matrix estimation, you will do what I would call simple linear regression. And then after that, you use that to do prediction. Okay, so just to remind ourselves, this was the transformation we did in the previous step. Now I had this superscript 1, which I didn't emphasize there, but now I will emphasize. I could do this like this, or I could shift everything by one more thing, like starting from 2, or starting from 3, or starting from L. Okay, so L versions of matrices, effectively a little bit shuffled. So I got L of them. For each of these matrix, I will do matrix estimation. And then what I will do is that in that matrix, estimated matrix, this is the last row. And these are all L minus 1 things before that, effectively, for this element in every column. And I will think of these as features and this as target. And I will do linear regression. That is, and let me call that beta k. And then now I'm going to predict for t plus 1. Effectively, I'll find k as this because where it lies. So I'm just simply looking for the last L minus 1 things and use the right model for that. That's how I'm choosing k. I go and look at my last L minus 1 things. Then I project them on the column space of my denoised matrix. And after that, with that projected vector, I just do inner product, and I get the value. Okay, so nothing really complicated. So it's effectively same as before, but with this one linear regression step. Now, this is where this worked really well in practice. And so we were wondering, why should it work well in practice? Turns out there's a really interesting fact that is last row being a linear function or approximately linear function of all other row for all of these latent variable model is true. And it's remarkable that it's true. So at least, yeah, we found proof is simple, but at least it was lots of experiments that drove us to this conclusion, and that was surprising to us. And you get what you hope for is you got error which scales with noise, but there's universal constant, and there's 1 over p, which is the missing value. All right, I think I'm literally at the end of the things do well, as one would expect. And the last thing is with synthetic control. I think I'm not going to go there. Again, it turns out to be effectively a matrix estimation problem, but with many time series. So for example, if you go back to the previous examples where instead of having one time series, now you have multiple time series, and now you want to use multiple time series along with the time series structure to do estimation for the target, you could use the same method, that you just keep stacking the lags. When you do that kind of thing for the world of synthetic control, you get what you want. It seems that if you did not do the matrix estimation, the traditional methods actually do terribly. That's the only piece of information I'll leave. And with that, we'll sort of stop here. Thank you.
Time for a question or two while the next speaker is ready.
Yes. That is correct.
So without regularization, won't it mess it up? Like it's just unfortunate.
So short answer is no. A long answer is regularization can help. At least in experiments we find that. We don't know exactly when it's doing better. Of course, when you have a smaller amount of data, that does help, as you would expect. But I don't have a good conclusive answer for that. Yes?
I think in many time series, F changes slowly with T, and a characteristic of these matrix completion methods, I think, is that the rows, you could reorder the rows, and you would get the same estimates. So it seems like there's some information that could be retained that's being thrown away. Do you think there's an improved version of this method that would do something like that?
A good question. So there's only one type of structure that you're retaining, which is by every column has effectively, quotes and quotes, recent history. And so even if you shuffle them, it's not clear that you really fundamentally lost things if I'm thinking from the lens of linear regression or any regression function. So I don't know how to answer that question.
I guess the structure that I'm thinking about in the context of matrix completion would be that the latent variables on the rows should change slowly with the row number.
Yes. great question. Maybe in interest of next speaker's time, I'm going to take it up. Thank you.